We turn now to the topic of the mean value theorem, and if you're following along in the Thomas textbook, this is section 4.2. So let me just put up the statement of the mean value theorem along with a picture. So the statement is, if f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists at least one number c in the interval open ab, such that this equation is true. As usual, the words are denser than the picture, so I've put up the picture, and hopefully this is a little bit more illuminating. So let's suppose that I have a function y equals f of x. That's what you see here in purple, and as we have two numbers a and b on the x-axis. As you know by now, those two numbers correspond to points on the function of the form a f of a and b f of b. So if I were to draw a secant line, that's this green line here, through those 2 points, a f of a and b f of b, what I would get is a line whose slope, in other words, the slope of that secant, just using the slope formula, is going to be f of b minus f of a over b minus a. That's just the usual y2 minus y1 over x2 minus x1. And that's exactly what you see here. So the assertion by the mean value theorem is that somewhere inside this, in the interior of this interval, in other words, that's why we have the function is defined on the closed interval ab, including its endpoints, but it's said to be differentiable on the open interval that does not include the endpoints. Somewhere in the interior of this interval, there's a point where the tangent line, that's this green dotted line, is parallel to the secant line. In other words, has the same slope as the secant line passing through those numbers, so passing through those points. So that's what you see here in the final statement of the mean value theorem, is that somewhere the derivative, there's some point c where the derivative is equal to this expression which gives the slope of the secant line. That's just stating that at the point c, the tangent line has the same slope as the secant line, or is parallel to that secant line. It's worth noting that what is being asserted is the existence of the number c. In other words, it's easy to look at this picture and say, oh, I understand the picture, and not realize what it is exactly that the mean value theorem is asserting. What it is asserting specifically is this number c. It's saying somewhere in this interval there is a number c such that this statement about the derivative at c is true. So it's not really asserting the existence of the tangent line, it's asserting the existence specifically of this number in the interval ab. And by the way, the theorem states that there exists at least one c. I could draw the picture slightly differently, where let's suppose that I have something like this, where let's put in, if that's the secant line between 2 points a and b like that, I won't even put the axes in, I'm just going to draw in the two endpoints. What you can see is that here there would be two tangent lines that are parallel, and therefore there would be two numbers, let's say c1 and c2, where the tangent line is parallel to the secant line that I'm shading in here. And that's what the theorem asserts. It says there exists at least one c. It doesn't foreclose the possibility that there's more than one. So there's the statement of the mean value theorem. Now, there is actually, historically this came earlier in time, but there is a special case of the mean value theorem, which is called Rolle's theorem. And what this states is, again, we assume the same conditions about f of x. We say that if f of x is continuous on the closed interval ab and differentiable on the open interval ab, and now we're going to set the condition that f of a equals f of b, then there exists at least one c in the interior of the interval such that f prime of c is 0. Now what's that all about? What that's saying is that here I have both fa and fb. I've set them equal to each other, and what that means is that when I draw the secant line through them, I'm just drawing a flat horizontal line. So this is just a more restrictive version of the mean value theorem, where fa and fb are equal to each other, so the slope of the secant line through them is 0 instead of just this arbitrary expression here. If f of b equals f of a, then fb minus fa would be 0. So This is really just a special case of the mean value theorem. The reason to know it is, first of all, it's one of those facts that people learn in Calculus 1. Second, historically, Rolle's theorem came first. Rolle's theorem was it's not as if someone came up with the mean value theorem and then Rolle said, I wanted my own theorem, so he came up with a special case. That's sort of backwards. What happened, rather, was that Rolle came up with this theorem, and the mean value theorem was proved as a generalization of it. So historically, Rolle's theorem came first, but now that we have both theorems, you can think of Rolle's theorem as just this very special case of the mean value theorem.